In this video, I will show an algorithm that generates any random variable by flipping a coin repeatedly. Suppose that we are given an unbiased coin, meaning that the probability of heads and tails are both equal to 1/2, and we are going to use this coin as our source of randomness. And let's say that we have a random variable x with the probability of mass function p1, p2, p3 up to pm, which are assigned to values x1 up to xn. And the goal here is to find an algorithm that generates the random variable x by tossing the coin repeatedly, meaning that by looking at the random coin tosses, we have to decide what x should be. And because the tosses are random, the outcome of the algorithm is also random, and its distribution must match the distribution of x that we are interested in. And secondly, we want to ask if our algorithm is optimal in some sense. For example, can we make the number of tosses minimum? Before I present the solution of this problem, first I will make some observations. The first observation is that the labeling of x1 up to xm doesn't matter for us. This is because whatever those labelings are, we can always assign xi to I and then generate a random variable for these labelings, and after relabeling we can just generate the random variable with those labels. So therefore the only thing that matters are the values of probabilities p1 up to pm. And secondly, some cases are easier than the others. The first easy case is p equals 1/2, 1/2 case. And we can generate this random variable by just tossing one coin. If we assign heads to 1 and tails to 2, we see that the distribution of this assignment is exactly 1/2, 1/2. And in the second example, we have p equals 1/2, 1/4, and 1/4. And because each probability is a power of 1/2, and because the largest power is 2, because 1/4 is equal to 2 to minus 2, we can toss two coins and assign the sequences as follows. HH and HT are assigned to 1, and TH, tail and head, is assigned to 2, and TT is assigned to 3. And if we write down the probability of each assignment, we see that we exactly match 1/2, 1/4, and 1/4. Therefore, in this case, again, we can generate a random variable by just tossing two coins. We notice that in the second example, we can actually do better than two coin tosses. This is because HH and H2 are both assigned to 1. And this means that after the first coin toss is heads, we don't need to see the outcome of the second coin toss, and we can just stop after the first coin toss if it comes out heads. And if n denotes the number of random tosses, its expected value, which is the average number of tosses, is equal to 1/2 times 1 plus 1/2 times 2 equals 3/2. And this is strictly less than 2, which is the average number of tosses for the first algorithm. Therefore, there might be different algorithms with different number of average tosses. So after these examples, we can formalize our problem. We realize that after each toss, we do one of two things. The first thing is we stop and declare x to be some little x, or we decide to toss another coin. Since this decision is sequential, we can formulate it as a decision process over a complete binary tree. And complete binary tree means that we have a binary tree, and after each node there are either two branches coming out or no branches coming out. The nodes that do not have any children or any branches after that are called leaves. For this example, V1, V2 up to V6 are leaves, and the others are regular nodes, non-leaves. For a given distribution P, we should form a complete binary tree such that all of its leaves are assigned to some values of x, so that whenever we reach a leaf, we stop and declare x equals little x. And this means that every algorithm has a tree T and a function f from the leaf set V. For this example, this is from V1 up to V6 to the alphabet x, which is 1 to n, 1 to m, so that the probability of f of v equals x is equal to px, so that we guarantee that we generate random variable x. And furthermore, we also know the distribution of leaves random variable v, and this is because it is obtained from the random coin tosses. If v its probability is equal to 1 over 2 to length of v. So let's see some examples. V1 has a length 2, and it is reached after 2 h's, and its probability is 1/2 times 1/2, which is equal to 1/4. And secondly, and similarly, probability of V2 is equal to 1 over 8. Before we explain the algorithm, let's first explain the binary expansion. Given a distribution, we write down each probability pi as its binary expansion. We can always do this by long division, just like what we do for the decimal case. The only thing that differs is the base. It becomes 2 rather than 10. Let's see some examples by what we mean by binary expansion. 1 over 4 has the expansion 0.01. 3 over 8 has the binary expansion 0.011. We can check this by summing the contributions from ones. It is 1/4 plus 1 over 8, which is equal to 3 over 8. And there are also cases where the p has an infinite length of binary expansion. If p is equal to 1 over 3, its binary expansion is 0.010101 repeatedly. And we can check this by geometric sum. And now we express pi from the contributions of ones. Let's say that because zeros has no contribution to this sum. From the binary expansion, we see that any pi can be written as sum of 2 to minus lj's, and here lj's are some integers, and they will be depths in our binary tree. Again, let's see some examples. 1 over 4 is expressed as 2 over minus 2. Therefore, its length function is just 2. And here 2 is the location of the 1. There's only a single one, therefore, and its index is 2. And for example, p equals 3 over 8 has 2 ones, and their locations are 2 and 3, therefore the length function is 2 and 3. And similarly, 1 over 3 has ones for the even locations, therefore its length function is 2, 4, 6, 8, and so on. Let's see how we construct the tree and the assignments f. Given p vector, we find the corresponding length vectors L1 up to Lm, and we concatenate them to get a combined length function L. And the assignment function f just inverts the index I from the Li's. Let's see what we mean by this in the following example. P is 1/2, 3/8, 1/8, and the corresponding length functions for each PIs are 1, 2, 3, and 3. And the combined binary tree is given on the right hand side. It has length 1, 2, 3, and 3. And what we do is we assign the length 1 to x equals 1, length 2 to x equals 2, and there are two trees. We assign one of them to x equals 2 and the other one to x equals 3. And the function f and the binary tree is given by this here. In the second example, let's say that we have p equals 1/2, 1/3, and 1/6. And the corresponding length functions are 1, all the evens, and all the odd ones except 1. And as you see, the overall length function is actually all integers used once. And if we do the assignments, we see that depth 1 is assigned to 1, x equals 1, depth 2 is assigned to x equals 2, and all the odd ones starting from 3 are assigned to 3, and all the even ones starting from 2 are assigned to x equals 2. And the assignment and tree looks like this. But we are missing something. We should also show that such a binary tree always exists, and this is proved by Krauss inequality. It states that a complete binary tree with length function L exists if and only if the summation of the length function values, the summation of 2 to minus length function values is equal to 1. Let's see what we have for our application. PIs are already given by summation of 2 to minus LJs. And because the sum of all PIs is equal to 1, we sum all of these sum of 2 to minus LJs. And overall, we have some 2 to minus LJs. And therefore, the combined length function actually satisfies Krauss inequality, and therefore, it always defines a complete binary tree. And here, recall that all L super i's are vectors, and we can also open them up. And after that, we say that the size of overall length function is n. And secondly, we also need to check that this algorithm always generates x exactly, its distribution match. In order to do that, first we let v be the random leaf of the tree, and as we showed, its probability is equal to t2 minus length of little v. We assign each v to some x according to the length function of the tree. And after this, we can write down the probability of x equals little x to summation of 2 to minus lv's, so that f of v is equal to x. And according to the definition of f, this becomes exactly px, matching the distribution of the random variable x we are interested in. Therefore, this algorithm generates x. So let's summarize the algorithm. We construct the binary tree with the length function L by writing down the binary expansions of each PIs. We start from the top node and we move along the tree according to the random tosses. And we stop if a leaf v is reached. And we return the function f of v as the realization of x. Again, to explain this better, let's see some examples. We are using the same examples as before. In the first example, p is equal to 1/2, 3/8, and 1/8. After applying this algorithm, we get the tree and the assignments as shown on the left. And let's see that the random coin tosses are heads, heads, tails, and heads. we see that after the first coin toss, we already reach the leaf v equals 1 and it is assigned to x equals 1. Therefore, we stop after the first coin toss. In the second random coin tossing, let's say that we have TTH, and TTH stops at the leaf v equals 3 and it is assigned to x equals 2. So if this happens, we declare x is equal to 2. And because the random tosses are random, the outcome is also random. So this is also what we are looking for. In the second example, we again have the distribution 1 over 2, 1 over 3, and 1 over 6. It has an infinite length binary tree with the given with this assignments. Let's say that HTH is a random coin tossing. If this happens, we stop at the leaf v equals 1, which is assigned to x equals 1. Therefore, if this happens, we stop after the first toss. In the second example, let's say that TTTH is a random coin tossing, and this sequence stops at the leaf v equals 4. Therefore, the number of tosses is 4, and the outcome is 2. Finally, we will talk about the performance guarantees of this algorithm, and this is proved by Knuth and Yao in 1976. First, we will define the entropy of a random variable x, which is given by summation of little x pxx times logarithm base 2 1 over pxx. The entropy of a random variable measures how many bits we need to represent the random variable x. In short, it is used in source coding most of the time, and this problem is also very close to source coding. Let En be the expected number of tosses. They show that for any run algorithm that generates x, the expected number of tosses is at least entropy of x. And secondly, they also show that this algorithm above guarantees that the expected number of tosses is at most h of x, the entropy of x plus 2. Therefore, this algorithm always operates between entropy of x and entropy of x plus 2. And thirdly, they also show something stronger, and it is that there are some random variables x, so that h of x plus 2 is optimal. Therefore, this algorithm is optimal in terms of the worst case performance. We cannot find any better upper bound that applies to general random variables. And this is the end of the video. Thank you.